All right, my statistical friends, let's do our last chapter on distributions. This week, we're going to talk about sampling distributions. A sampling distribution is the distribution of the results that would occur had all possible samples been included in the data collection. Imagine that you collected sample after sample after sample after sample until finally the whole population was involved. Then your data would represent everyone. Now, that's not usually possible, but when we can collect multiple samples, we get a better idea of what that population looks like. And really, that's what statistics all comes down to. It's being able to make inferences about a population. When we're sampling, we want the largest and most representative possible sample. The larger the sample, the more representative our data, and the more it tells us about the population. With a large enough sample, outliers don't affect our data anymore because you're going to have outliers that fall to the left and the right of the mean, and they're going to cancel each other out. The sampling distribution of the mean, which means if we were to plot, like we did in previous chapters on a distribution curve, all the means of all the samples that we collect, eventually, that's going to mirror the distribution of the population mean. And the standard error of the mean is something that expresses how the sample means vary from sample to sample. Now, when we are lucky enough to know the population mean and have a variety of samples, we can do some more accurate calculations. It's very rare that you're ever going to know what the mean of population is. Sometimes this does occur in business, though. Imagine, for example, we're working for a clothing company, and we know on average how much thread is used to create this specific shirt across all locations because we know the amount of thread used. What we don't know is on average how much thread each individual shirt from each individual machine at each individual factory contains. So this would be a rare example when we would know that population mean and we could collect sample means to calculate a z-score. The difference in z-score calculations when you're using samples and you know the population mean is that you're going to divide by the standard error of the mean instead of simply the standard deviation. Let's practice that in Excel. Here we have an Excel sheet that has 18 customers listed, and this is their percent of satisfaction. Notice here that I've left their percent of satisfaction represented as a decimal. Excel doesn't like to use its statistical package on things when you leave them in percentage form. It works better with decimals. So first things first, let's calculate our descriptive statistics. Let's go to our statistical package, descriptive statistics. The input range is going to be our customer satisfaction data. And the output range, I'd like it to start printing things in cell E5 this time. And I'll hit OK. And our z-score here is equal to the average of the sample, which we know here is 0.45, minus the mean of the population, 0.81, divided by the standard error, which is the standard deviation, divided by the square root of the size of your sample. Here in Excel, the easiest way to do this is to write your sample size, which is 18, raised to an exponent of 0.5. Raising something to an exponent of 0.5 is the exact same thing as taking the square root. Note here that I used an extra set of parentheses because I want to make sure that Excel knows that the square root of 18 is what I want to be dividing the standard deviation by. And oh my goodness, that is really low. Remember, we know that over 99% of our values fall between -3 and +3 standard deviations. Well, how can this be? Well, our average satisfaction for this particular store or this particular sample is less than half the mean of the population. That means we've got a lot of outliers here that pull the score really far down. Now, how does this reflect what we're talking about? This is just one mean. And we know that when we collect the means of multiple samples, eventually we're going to get enough samples that all of those extremes balance each other out. So this is one of those extremely low samples. And somewhere out there, if that average mean for the company is 81% satisfaction, you've got some really high sample stores to balance things out. In this chapter, we talk about the central limit theorem. And the central limit theorem states, not just in this textbook, but everywhere, that as the sample gets large enough, as we include more and more and more sample stores, for example, with what we're talking about now, the sampling distribution of the mean is approximately normally distributed. That means for our -5 minus standard deviations away from the mean, you've got the really high ones out there that will balance things out. And here's a crazy fact. When it comes to data, when you have a sample size of at least 30, things start to become normally distributed. Odds are that if we randomly selected 30 stores, one of which was this store, that the other 29 randomly selected stores would actually balance this crazy low score out. Now, another thing that your chapter talks about is calculating the error under the curve to get probabilities of individual z-scores. So let's look at how to do this in Excel. To do this, we need to calculate our z-scores. And these are individual data z-scores, not z-scores of the mean. So we're going to go back to our old formula that our data point minus the sample mean divided by the standard deviation is our z-score. All right, now how do we calculate the probability of less than or equal to? Well, we're going to use the norm s dist command, equals NORM. See it? There we go, norm s dist. And this means we want Excel to do this calculation using this normal distribution. It asks us for our z-score, which we provide for it in D2. Then it asks for us cumulative, true or false. To calculate that area under the curve, the way your textbook has it set up, such that you're calculating the probability of this score or lower, we want the answer to be true. Now, does this make sense? Let me turn these into percentages. We're saying right here that there is a 98% probability that the customer satisfaction score will be 0.99 or lower. Well, yeah, that makes a lot of sense. What's the probability that the customer satisfaction will be at least 38%? Well, 40% probability that they're going to be 38% satisfied or less. So this is our wrap up of thinking about distributions. Please let me know if you have any questions.